In this mini lecture, we're going to talk about an application of magnetic forces and our cyclotron radius in something called a mass spectrometer. A mass spectrometer is an important tool in chemistry and in physics. Unknown substances can be heated and ionized inside this ion source here, and then passed through into our device here, which is our mass spectrometer, in order to be identified and classified. This is a schematic of how our mass spectrometer works. You take your sample and you put it into the ion source. That gets it really hot and it breaks it apart into its constituent pieces, and you inject it quickly through our velocity selector, which selects only for a particular speed of particles that are moving within this part of the apparatus. And then that particle enters into the main component, the main chamber of the mass spectrometer. And because there's magnetic field within this main chamber of the mass spectrometer, and because our particles are charged, the path of the particle is going to be curved within this magnetic field. So you can measure the radius of the path of your particle within this magnetic field. And when you do that, you can determine the mass per charge ratio of your specimen. This ratio is known for a bunch of different elements and compounds and molecules. So you put your sample into the ion source, you spit it through and into the mass spectrometer, you get the mass per charge ratio. Essentially, what it's doing is it's figuring out kind of the radius of this curved path, which then tells us the mass per charge ratio. Let's say, for example, you put your specimen into the ion source, it's ionized, and it spits out a beam of that material. It goes through the velocity selector, and then it enters into the main chamber of our mass spectrometer. And because that particle has some charge, it's going to execute a curved path within here. And then we can determine the radius of this curved path here. Okay? And the radius of this curved path, actually this is twice the radius, so it's the diameter here of the curved path of our particle inside the mass spectrometer. Getting this distance here will tell us the mass per charge ratio of our specimen. Now what I've drawn here is the path that a positive charge would take inside the mass spectrometer. So let's imagine that we have a proton. So our proton coming in here could execute this curved path. Let's say right here, we've got our protons, positive charge. At this very point here, its velocity vector is pointing in this direction. The magnetic field is out of the page. So my fingers point in the direction of the magnetic field, out of the page. Oh, my thumb is pointing down in the direction of the velocity vector. And so my palm tells me the direction of the magnetic force. And so the direction of that magnetic force is pointing in to the center of this curved path here. And that's what's allowing this particle to execute this curved path in this direction. So it's going to enter here. The force will always be directed inward towards this curved circle. And eventually, it's going to hit a wall, or it's going to hit a measurement device right here that's going to detect the radius, essentially, of this curved path, and from that infer the mass per charge ratio. When our particle enters into the mass spectrometer, it must be given a velocity. So this component of our mass spectrometer, called the velocity selector, only lets particles into the main chamber of the mass spectrometer if those particles have a particular speed. So if the speed of all particles entering into our mass spectrometer is fixed, then the radius of the curved path will be proportional to the mass per charge ratio. Okay, so maybe we have another particle that has a different mass per charge ratio. It's going to enter through the velocity selector with the same speed, but when it comes out over here into the main component of the mass spectrometer, because it has a different mass per charge ratio, it's going to execute a different curved path within here. And then you could determine the distance, twice the radius of that curved path, the diameter of that curved path, and then determine that particle's mass per charge ratio. This velocity selector has an electric field that is perpendicular to a magnetic field inside it here. Only the particles for which the electric field equals the magnetic field are able to travel in a straight line through this velocity selector without being deflected to one side or the other inside the velocity selector. So within this device, if the electric field acting on that particle equals the magnetic field on that particle, then that particle is just going to travel straight on through and not be affected by the electric field or the magnetic field. And then it will enter into the mass spectrometer, main chamber of the mass spectrometer here. So the velocity selector only picks out particles, no matter what your substance is that you're putting in the ion source. It only picks out particles that all have the same speed. So you have that one control parameter that's fixed, the speed at which the particles are entering into the mass spectrometer chamber. How do we find the velocity specifically within the velocity selector for all particles that travel through here unimpacted by that perpendicular electric and magnetic field? Well, the electric force has to equal the magnetic force in order for them to go straight through the velocity selector without being deflected. Now previously, we saw that the electric field was equal to the electric force per unit charge. So that says that the electric force is equal to the electric field times the charge. So our electric force here will be our electric field times the charge, and that equals our magnetic force, which is Q V B sine theta. And in this case, if the velocity vector of our particle is perpendicular to the magnetic field vector of our particle, which is what we want, then sine of theta, theta is 90 degrees. If they're perpendicular, then sine of theta is 1. So we see here that Q cancels on both sides. So we've got E is equal to VB. So if we solve this for V, V is equal to E over B. So only those particles that have a speed set specifically by the ratio of the electric field to the magnetic field within the velocity selector are able to pass through into the mass spectrometer. Once our particle enters into the main chamber of the mass spectrometer, it's experiencing a magnetic force that's equal to QVB sine theta. Okay, now again, it's executing circular motion here because of that magnetic force that's always directed inward toward the center of its curved path. Remember last semester when we talked about circular motion? This magnetic force is causing circular motion. This particle is going to be experiencing a centripetal acceleration as it's going around this path. And that centripetal acceleration is caused by the presence of this magnetic force. That particle then experiences a centripetal force, which is equal to its mass times its centripetal acceleration. Okay, so it is this magnetic force that's causing this centripetal acceleration. So we can set these two equal to each other in order for this particle to execute and continue to execute the circular path here. Its magnetic force has to equal its mass times centripetal acceleration. So FB will equal FC. So our magnetic force here was QVB sine theta, and that equals the mass times the centripetal acceleration. Now we saw last semester that the centripetal acceleration is equal to the velocity squared divided by the radius of that curved path. Here we're also going to say that the velocity vector is perpendicular to the magnetic field vector. So sine of theta, theta is 90 degrees, sine of 90 degrees is 1. So we've got QVB is equal to mv squared over r. So let's solve this for r, the radius of this circular path. So I can multiply both sides by r. So RQVB is equal to mv squared. And then I divide both sides by qvb. Divide both sides by qvb. R is equal to m. I've got v squared over v, so that just becomes 1v on the top. This v cancels out with one of those, over qb. So the radius of the circular path of the particle inside the mass spectrometer is its mass times its speed divided by its charge times the magnetic field here inside this chamber of the mass spectrometer. Sometimes we call this the cyclotron radius. And we can also use this expression to get the mass per charge ratio of any particle that's inside the mass spectrometer, given that we know what this diameter of its path is, which is twice its radius. So the mass per charge ratio, we just want to solve this equation for m over q. If we solve this equation for m over q, we find that m over q, the mass per charge ratio, is equal to the radius of the circular path times the magnetic field divided by the speed. All right, so by setting the magnetic force that our particle experiences inside the mass spectrometer to the centripetal force that it experiences as it executes this circular path, we can find either the radius of this circular path inside the magnetic field, or we can find the mass per charge ratio. Let's quickly apply our equation for the mass per charge ratio in order to solve a problem. And we're going to have a charged particle that enters the magnetic field of a mass spectrometer at a speed of 1.79 times 10 to the 6 meters per second. It subsequently moves in a circular orbit with a radius of 16 centimeters, or 0.16 meters, in a uniform magnetic field of magnitude 0.35 teslas, having a direction perpendicular to the particle's velocity. We needed to use that in order to get this expression here. The magnetic field is perpendicular to the particle's velocity. Find the particle's mass per charge ratio. Okay, so you just plug in these numbers here, R, V, and B, into our equation for the mass per charge ratio. And for these quantities here, we get a mass per charge ratio of 3.13 times 10 to the minus 8 kilogram per coulomb. So that's our unit of the mass per charge ratio. We've got the mass in kilogram, we've got the charge in coulomb. This particular mass per charge ratio is for tritium, T-R-I-T-I-U-M, and it is a radioactive form of hydrogen, and it's produced in atoms when cosmic rays collide with air molecules. Cosmic rays are high energy nuclei that are traveling through space. Every element, every compound, every molecule that we know of has a unique mass per charge ratio. So once we put that specimen into a mass spectrometer, using just this physics right here, we're able to determine what that substance is.